Okay, so let me recall a little bit of what we did. So we were thinking about this kind of layers. And the point of last talk was we choose a Lagrangian. This one in this case, and this one. So choose what I call reference Lagrangian. And so this is a Lagrangian. So manifold, it has this infinite algebra. So I denote it by some graded vector space with this MK operation. Okay. And then we looked at the Markov-Tan solutions of this AP algebra. So what was the Markov-Tan? Markov-Tan element, or weak Markov-Tan element, was an element in the degree 1 plus satisfying this M0 plus M1B plus M2BB plus M3BBB. So usually we write this as, this is a convention, M of exponential of B. Exponential usually have to have some fraction, I mean, you divide by n factorial, but this is not commutative version, so usually this kind of convention works well. Okay, so this is just a notation, and we want Markov-Tan equation is, so yesterday we saw Markov-Tan equation Lie algebra, there was differential and V bracket, then it's 0, right? So usually we want this to be 0, but when we say weak, then we want it to be some multiple of unit. So this guy has a unit, and we want it to be some multiple. So this the coefficient is an element in non-coupling, and also depends on B. So we just write this as W of B.
And the unit is something you choose, or there is some uniqueness?
You have to prove that it exists. So, yes.
But is it unique?
It's unique.
It is unique.
Right. But the problem is actually it could be a homotopy unit. Only in unit. So whenever you have an infinite algebra, you can also construct the homology version of infinite algebra. So you can put all these infinite structure on homology, and this guy has a unit usually. On some constructions, this also has a unit. So, but the unit is supposed to represent just the fundamental class, the Lagrangian. So, okay, so we have this weak Markov-Tan equation.
My question is because of the following. So I would like to understand the dependence of the potential on the unit. So because you wrote the way of defining the potential is using the unit. So if you have a different unit, you may have a different potential. Am I mistaken?
No, because these infinite algebras are infinite isomorphic, infinite quasi-isomorphic. So you can do everything here, actually.
So that equation that you wrote.
Yes. So this kind of quasi-equivalence preserves the potential value, although it might change. So Markov-Tan solutions of two are related, and when you can send Markov-Tan element to a Markov-Tan element when you have a quasi-isomorphism.
And the space of Markov-Tan elements have the same dimension because the space of Markov-Tan elements
they are.
Is the source space. So your potential has a source that is the space of Markov-Tan elements.
Right. So the solution space, they are isomorphic. So there's an explicit formula if you have an infinite functor. And it's not actually not linear. It also involves some exponential expressions. Okay, so we have this Markov-Tan element, and then what this enables us to do is we can deform. So this is deformed A infinite L0. So MKB was when you have inputs from x1 to xk, then so this is the sum of all possible expressions of B x1, B xk, B. So original inputs are all there, and then you just insert all possible B's and take the sum of all expressions. And this defines an infinite. Okay. So usually, so this B, you can think this. So in cohomology, this what is it? It's in H1. So it's if you look at like a tubular neighborhood of Lagrangian, H1 is like a closed one form. So it's like the image of graph of closed one form is this is like cotangent bundle, and graph of one form is like nearby Lagrangian. So this somehow this deformation is in that sense. But also in this case, the B's we'll choose are like these angles at self-intersections. And when you have self-intersections, then somehow this B somehow represent the surgery, deformation by surgery. So this Markov-Tan equation usually look at deformations, and the deformations are either formal way of seeing surgery or kind of nearby Lagrangians. So that's kind of the intuition that we have. Anyway, so just if you satisfy this equation, then we have another infinite. Okay, so we have this, and then we had this assumption that this V1 element of V1 satisfies the Markov-Tan equation. So that means, say, basis. If we choose a basis, so this degree 1 class, we choose a basis and take a formal linear combination. So xi is some Novikov parameter. It should have some positive energy, but anyway, so let me skip this part. And then we want, so any linear combination satisfies this weak Markov-Tan equation. So that's our assumption. So we have kind of good deformations in the degree 1 direction. And then what we observed was that the derivative of this potential in one of the directions of the variable is like taking derivative of this here. And so the derivative will hit one of the B's, and when you differentiate one of the B's by xi, then you get this capital Xi. So this is sum of m of B, and then when you take derivative, it becomes xi, and the rest is still B. So this is nothing but m1b of xi. And so the critical point of W corresponds to xi's m1b cycles. And after after some argument, you can say that xi is non-trivial. So flow homology is not. So M1B homology is not zero. So critical point, the flow homology, non-zero flow homology. The other one also works. If it's not a critical point, then the flow homology vanishes. I think we should still have unit here, but anyway. So that's what we did last time. Any questions?
I still don't understand the nature of W.
Nature of
So what is the, this is a function from which space to which space? What values it takes?
Okay, so let's denote MC, the whole Markov space, whole solution space.
And this has, and what is that? This is a module over the Novikov ring or what?
Yes. So it's a subspace. I mean, it's a subset of V1. And as in yesterday's talk, you can also define gauge equivalence between them. And we are kind of in our case, these are really generators, so they don't have any gauge, non-trivial gauge equivalence. So in this talk, we'll just ignore this part. And
so this is not a complex vector space of finite dimension.
You mean this V1?
Yeah.
So in this case, we are really, this is a circle, and we are really looking at H1 of LC. So this is one dimension. But so the immersed version and this torus version are a little bit different because the variables are it has to be exponentiated because of the holonomy. In fact, yeah. So what I'm going to explain works here. You need some modification because of this exponentiation. So this was like t to the e to the I zeta, and so now this holonomy variable. Anyway, so let me say this one for this blue L. We call that the flow homology of this chain complex of this L in this immersed Lagrangian case. It had you can choose like Morse complex, so that it has a point class and the unit class. Maybe this is point, and this is unit, and then you have this self-intersection point. So you have x, y, z. And then you have these opposite angles, x bar, y bar, z bar. And over lambda. So this is over lambda. So that's, and so among this, the degree 1 class is these one, x, y, z. Or you can also include point, so x, y, z and point. So you can choose, in fact, what I'm choosing is just x, y, z. So, and then they satisfy Markov-Tan equation. Is that clear?
So there are you meaning H1 is the equation is in lambda? System.
Yeah, maybe lambda. Yeah, I mean, in this case, it's exact, so you can reduce coefficients to C, but going from lambda to C, this is kind of very delicate question, so you have to be very careful.
That was
Yeah. Yeah, it's, this one, it's not a simple question. Okay, so let me, so in some cases, there are cases where it looks like dimension 3, In this case, inverse curve is dimension 1, but it behaves like dimension 3 because there is a degree convention. You can give a grading so that this guy has grading 0, grading 3, grading 1, and grading 2, because the product of xy is z bar, and product of z bar is point, and so on. So the sum of the product preserves this grading convention. So why do I say this? So in kind of dimension 3, this Markov-Tan equation can be related to this Jacobian idea. So for this, we need to assume that we have a pairing. So if we have a pairing. So non-degenerate pairing, non-degenerate, and so this is a pairing on infinite algebra. So the best possible scenario is the following cyclic symmetry. So mk of x1 through xk, and then you pair with xk plus 1, and you can kind of rotate the inputs. So now it starts from x2 to xk plus 1, and then x1 goes to the last part. Suppose that we have a pairing with this property, cyclic symmetry. This is called Calabi-Yau category.
Should taking G2 graded.
Now let's say we have some grading which of degrees. We have this kind of grading. Let's assume this. This is special case.
I think it should be one Calabi-Yau.
Well, look at this. The unit pairs with point. This pairs with this. It's not geometric dimension. So in this case, we can define another potential different from that W. So define this psi B. This is 1 over k plus 1, and mk of B paired with B, and sum of all k. So there are two potentials, and I think physicists call it like space-time. That's space-time potential, and this is world-shape potential. But they have different names. Anyway, so let's look at this one, and let's look at let's take a derivative of this guy. And the derivative is going to hit either one of the b's here or here, right? And then because we have cyclic symmetry, if we take a derivative this here, then we can rotate and move it here, right? So you can say that this derivative actually hit only here. And then there are k plus 1 of them because this derivative can hit any of the b's here. There are k plus 1 of them. So that this quick fraction adds up to 1. And this derivative is nothing but, so if you take the sum of all k, then this is m of exponential b. And pairing with, this is capital Xi.
There's no sign when you do the permutation?
No sign, because these b's are degree 1s, and in shifted grading they are degree 0, so there is no. So you can see that the critical, this Jacobian ideal relation looks like this. And so this guy has degree 1, and nk has degree 2 minus k. So the sum is expected to have degree 2. And so degree 2, so this, to check that this is non-trivial, you only need to check pair with degree 1 and see if it's 0. So this critical relation, critical point equation corresponds to m of e to the b is wait, yeah, now the degree comes back and I'm sloppy here, so maybe 10 minutes, right? Maybe it's only integrated, so that it's either this one, so it's even, so these are odd, so these are even. So it's either these output will be this or this, but then this, the pairing of these guys, so x and x bar is like a point. The convention is that these two pairs to a point, so first one. So the pairing of this being 0 means that it's actually a multiple of unit. So it's a multiple of unit. So sorry, so let's make everything G2, mod G2. So it's just even odd. Then, right. But this is Markov-Tan equation. So this is Markov-Tan equation. So in fact, this equation means there is no other output. So this can be some even generator here or some even generator here, but this being 0 is the Markov-Tan equation, and that's coherent. So Markov-Tan algebra, we identify with this. If these have degree m, so if you restrict to the region where this vanishes, then this Markov-Tan equation will hold true. This is Jacobian. Any questions? Sometimes Markov-Tan relation can be expressed as the Jacobian ring or another potential P. And okay, so let's just say now this was a special case. Let's go back to the original case and just remark is that this x1, xm can be taken as non-commutative variables. So everything works in non-commutative way. So this algebra, you can say maybe NC. So at the end, what you get is some NC algebra, and you have this potential function WB, and I can prove that this potential function is a central, always a central element on this non-commutative algebra. the non-commutative version, which I just say it as a remark. Okay, then in all these cases, we have what we call localized mirror functor. So, what is this? So this is X, and we have this Lagrangian summation for the L. So this guy had this infinite algebra V and K. And this is a part of some infinite category. Let's say of X. Right? This L is an object of category, and the morphism space is given by this infinite algebra. Okay. And this, let me write it as a double L, bold L. This is because this is a special, it's special in the sense that we are going to use this Markov-Tan equation on this L. Then the claim is that Seoul with Hong and Lau is that there exists an infinite functor from higher category of X to the matrix factorizations of this WB. So it should send some Lagrangian K to a matrix factorization. Let's say PK. So this is P0, P1, P2, P0 is periodic, so that the composition is WB times identity. And so on. So for each Lagrangian, it associates a matrix factorization, and if you have two Lagrangians, say the intersection between them, then it associates morphisms between two matrix factorizations. P K1 to P K2 and vice versa. So what I will explain actually holds even in.
Here you take Lagrangians, or you take Lagrangians with local systems?
We're using the infinite category structure of higher category, so whatever we have used here. So if we have defined higher category for Lagrangian with local system,
And you still have it.
yes. So in fact, this, yeah, sorry, yes. No,
Well, so you say here you work with matrix factorizations, but your ring is non-commuted.
oh no, this was a remark. So sorry.
So matrix, so your W of B is finally what? Is it just a polynomial?
This is an element of lambda x1 through xn. So this was just the explanation that this is possible, and this was also, you can also do it non-commutatively, and this localized mirror functor works as well. But let's just stay in the commutative reason world, and then so the difference between this polynomial ring is that somehow we have this infinite expressions running around, so we need this Novikov ring, and then we allow infinite sums where this lookup, the tip, this guy, the exponent can go to infinity when you have infinite sums.
One more question.
Yes.
So if I allow local systems, so suppose that WB is of finite representation type. This is something that we could have.
Yes.
And then if I allow local systems, I can vary the holonomy. So I have some kind of modular objects of the Buchaya category. So what happens in the other side? Several Lagrangians are forced to go to the same matrix factorization. So how do you handle that you don't have any moduli on the
right. So let's say in the example of x plus q over x, you can factor this in any value, but it's only meaningful for critical values. Because let's say critical value is lambda, but you really want to factor this. Otherwise, if it's not critical value, you might get something, but that's always homotopy to 0. Does that make sense? So it's similar here. So you have this you can have Lagrangian and some local system over it. And if it's flow theoretically meaningful, flow common is non-zero, and you expect you get something non-zero here too. So that means okay. So as you said, this guy has this holonomy parameter into the I theta. So the matrix factorization, resulting matrix factorization will have one this parameter family of matrix factorization.
But maybe this is impossible because if it is finite representation type.
Right. But
this is not possible.
So this will happen in Jiangmin's talk because XYZ is tame, and so
yeah, but that is tame.
So in that case, we have a loops, but in the case of discrete or finite representations of matrix differentiation, their surface will be simple, so we will not have some closed curves, meaningful closed curves there. Then we only have up, which means every local system is just gauge equivalent to the trigger ones.
What means you only have arcs?
Arc.
In the you mean the Lagrangian is an arc?
Yeah, something like that.
Yes. But what if you picture a circle and then you decide to put a local system? That you can do it, and then it is a honest element of the Buchaya category where it goes.
To matrix factorization with some parameter lambda.
But if there is finite representation,
so maybe
it is impossible.
Yeah, this is possible.
maybe you can wait until the end of the lecture and we see an example. We see an example where this is finite type, and then we'll see what happens. So what I want to say is that this is actually the construction is purely algebraic, so it doesn't have to be Buchaya category. You just have some infinite category and some object whose morphism space is in algebra with this assumption of good Markov solution space, then there is always this counter.
The very last time the exponent equals symmetric situation, and then we have an arrow.
So when two Lagrangians intersect,
there's some orientation.
So there are two morphisms. This intersection can be interpreted as two morphisms. So this morphism will give this map. The other morphism will give the other. Okay, so let me. So let me show you an example, and so let's look at this example. So in this case, it's known that this is a mirror by Abuzaid, Oru, Kalsakov, or Timov. it's known that it's mirror, but this formalism will define this functor, and let's see how this goes. And this xyz, we interpret it as this triangle here. This X. And if you choose a Lagrangian, so this K, so we choose this K, we choose it to be this one, then this xyz triangle is kind of decomposed into two pieces. So here we have Z, and here we have XY. And somehow we want to say that this corresponds to the factorization of XYZ as Z times XY. But we could also, what we could also do is choose something much more complicated, which is homotopic to K. Let's say K prime. And in this case, we have like 4 intersections. And let's, if we give an orientation on this immersed curve, then, and on this non-compact curve, then they have even and odd parities. So let's say this is, so these two have the same parity. Let me call this P0 and P1. These two have the same parity, so this is Q0 and Q1. And so how do we construct this matrix factorization? Is by looking at this kind of maps. So what is this map? The map we are going to look at is so I'm going to look at this kind of map. So this this is part of B, right? So you can think of this as with one B, and this guy has with two B's. And you can give the direction so that it's B is on the upper boundary, and these guys have these directions. So what we're going to do is we count these kind of strips and say that this is a map from some intersection point to another intersection point. So P0, let's say this is let's say this coefficient is R, and let's say R module generated by K L intersection K of degree 0 of even degree, and P1 to be R module generated by L intersection K of odd degree, and this map from P0 to P1 and P1 to P0 is by counting this kind of maps. And let me show you how it works in practice. Now maybe let me erase K. This one is easy. So. And then you can see that this triangle, and we have this curve, and we have these arrows from P0 to Q0 with label Y, and from P1 to Q0 with label no label, and P1 to Q1 with label X. So I'm going to construct a matrix from P0 P1 to Q0 Q1, and this first triangle is Y. So this triangle goes to Y, and this strip for some reason obtains negative sign, and you get -1. So this from P1 to Q0, this is -1. This one corresponds to this one, and from P1 to Q1, this is X. And there is no map from P0 to Q1, so that's one matrix, and we can look for another matrix of no Z. So G will be on the other factorization. And so there is this triangle, this thing with two corners going from Q0 to P0. So that's XZ. So from Q0 Q1 to P0 P1. So this is XZ. And the same map from here to here. This is Q1 to P1. That's ZY. So this is ZY. And another map is this one. We have this. So this one with this purple line. So this is Z. And then if you multiply, then we get, if you multiply, Z, Y, those small characters, and this is XYZ, and this YZ minus YZ cancels. So intuitively, this W is count of a disk. W is a count of disk, and factorization is like a cutting a disk into two pieces. We're factoring the disk. And matrix factorization is a complicated way of factoring the disk. So when you multiply, you look at these diagonal entries. And diagonal entry means you start from here, go here, and then you come back to the original point. So if you glue these two, then you get XYZ. So that's original disk. Off diagonal is you start from here, but then you go somewhere else. So it's something like this, but you go to somewhere else. And then this guy always has some cancellation. It has always some cancellation, like it's cancelled here, so that it becomes 0. So, yeah, this is. And if you write this down algebraically, so FL, this functor sends K to floor homology of L and K, floor homology, floor complex of L and K, and then let's say even, odd, and this map, when you have generator alpha, and this, you send it to M1 B0 of alpha. So this means you allow all insertions of these and then alpha. And look at the output. So this is MK, sum over MK, BBBB, and alpha. So this B0 means you have B's in front, but you don't have B's on the back. So there is no B's, no B. Right? And because so these are B, you can insert B's because this is the Lagrangian L, this is Lagrangian K. It doesn't have B's. Well, you can also deform K too, but let's say we didn't deform it. And what I just showed is this matrix factorization is just this identity of infinite equation, this M1 squared 0. So this is original infinite identity, but because of deformation, now you obtain, instead of 0, you get this W of B of L minus W of K of 0. So from the upper side, when the disk bubbles up, you get W of B, and when the disk bubbles up in the K direction, you have WK of WK. Let's say this is 0. Let's say K does not bound the disk, no disk bounding K. Then you get the matrix. So when the disk bounds some disk, then this will be some constant number because we didn't put any variables for K. So it can be potential minus some critical value equals something squared. And M1B0, so this is M1B0. Also the opposite map is M1B0. And squared equals to W. So just the first infinite equation, deformed infinite. And the morphism, if you have K1, K2, and you have a point P, then the geometric map we use is this one. We have B's here, and then P here. And this was the generator of matrix factorization. This was the generator of matrix factorization for K1 and L. This is K2 and L. And by counting these kind of triangles, we usually get a map from some generator. So this is MF for K1 to MF for K2. And if P is even, then you get even map. P is odd, then you get odd map. And so infinite functor. So this one also you can write it as MB00 of some input and P. So this input and P. And infinite functor is MK B000 of many inputs. Oh no, one input and P1. So that's the first morphism level functor. Infinite functor has many higher homotopies, and K minus ones use MK, and this is an infinite functor. So it looks almost like Yoneda embedding because you see that just uses the natural infinite structure, but the point is that the object that we are using as a reference is actually curved, so it has this curvature, and somehow what it spits out is not chain complexes, but it's matrix factorization. You can say it's a curved Yoneda embedding. Any questions?
So your functor, so what is the role of the element B? So can you maybe summarize?
Let's summarize. So you can think of B as so in SYZ you have you have these Lagrangian torus fibers, and you have a mirror dual torus fiber, right? So if you want to see whole mirror space, you have to kind of vary the Lagrangian. But we fixed one Lagrangian, and instead we do formally. So we are kind of looking at formal deformations. So somehow we choose one and look at kind of formal neighborhood, and we're kind of looking at its mirror space. So this is, of course, the neighborhood of this torus is the nearby tori's given by harmonic forms. In this case, these formal generators give formal deformation space of this Lagrangian, and then, but it's curved because deformation space has this curvature W, and whenever you choose any Lagrangian, this disk is somehow factored into separate pieces.
So there is no choice of B. It was my question. So B is just a generic element of some space.
Right, but I think it's good to think of it as a family of nearby Lagrangians. That's great.
What are the assumptions of this theory?
The assumption was this V1 is a Markov space. The elements of V1 all satisfy the Markov-Tonic, weak Markov-Tonic.
Are you sure you're in the invertible polynomial case?
No. This is general. Just any infinite algebra. Any infinite algebra. Assumption is that any element of V1 satisfies this some multiple of unit.
So how often does that happen? For example, in the pair of bands, I think it happens.
So exponentiated version happens for toric manifolds. So you can also define explicit localized mirror function for torus. Let's say map case. Yeah, but somehow, yeah.
So does it behave well when you glue something?
Yes, you can also glue. Yes. So, for example, you could have instead of this, you could have something like this.
I think the question was, do you assume anything of X, or can you state the same statement arbitrarily to create the infinity algebras?
Yeah, this holds with only this assumption. Once you have this just, as you see, the construct, it's just using expressions using Markov-Tonic elements. Everything, the infinite algebra equation is used to define the function, like in unit algebra.
But then,
From what to what?
From what to what? So it's from this Markov-Tonic space. So this is WB, the space of these. So let's say the solution space of this equation as MC. Right? And so this W is a function from MC to lambda. And you give me B, then this is WB. WB is an element here.
the question was, what is the replacement of the Fukara category? If I say,
Just the infinite, in infinite category, if you have an object, then the home or O will have infinite algebra structure.
right, but it cannot be an arbitrary one, right?
It should be a one with a good Markov-Tonic theory.
And you say it's sufficient.
Hmm?
And you say it's sufficient to construct
Yeah,
a
right.
functor.
Yeah, so only this is used.
Yeah.
And this looks honest, but it implies vanishing of many things.
So because I would expect some property of generation. So this Lagrangian.
So yes, this is a functor, but I didn't say this is an equivalence.
No, but
So we know that this is injective on L something. So this sends morphism space to morphism space, but when is it injective? It's the homes related to L goes injective. So if it's not related to L, it will go to 0.
So this is small part, so should somehow know the whole Kaya category.
No, that's why we need gluing, because, for example, this four punctured sphere. So this one doesn't really capture this kind of curve, right? So this captures some curves here and some part of information of this curve and so on. So you need another Lagrangian to capture these kind of curves, and then can you glue?
What means glue?
So what means glue is
Each of the Lagrangians.
so this is L1 gives W B of L1. This one gives WB of L2. So and this was defined on the Markov space 1. This was defined on Markov space 2. And then you have to first check whether this Markov space has an overlap. And then when there is an overlap, then you can kind of take the fiber product of two matrix factorizations at overlap. So what you get is some global matrix factorization.
And is it necessary that the Lagrangian you start with is connected?
Uh,
So why don't you start straight away with the disjoint union of L1 and L2?
Because it kind of gives local chart. So, for example, this one gives C3 chart, this one gives C3 chart, and the mirror of this is gluing C3 to C3 in certain way, so that you get O minus 1 direction O minus 1 option.
Yeah, but what kind of construction you obtain if you start with the Lagrangian L1 union L2? Is this allowed?
Yeah, it's allowed. So, but anyway, so what you have is this MFW1. You have this map MFW2, and you just have these two maps. They're just two maps. And the question is, what's the relation between these?
My question is, what happens if you start with the disjoint union? How did the disjoint union relates with the procedure you?
Yeah, you get maybe product of these two categories. Just these. But somehow if you move this guy to here, suppose you do the actual surgery. So you do the surgery here. And this is like a double circle here, and you can move it. You get a double circle here, and somehow this double circle should be related to the double circle obtained by kind of doing surgery here. And then they can be this. So the variable x, y, g and x prime, y prime, g prime can be compared in the middle, and then you can check when they have an isomorphism, and they have an isomorphism if like x prime is 1 over x and y prime. You can check for which coefficient of this they are equivalent, and this is the relation that gives equivalence, and that's how you glue two C3 or lambda 3 charts to obtain this global mirror space. I can explain it. Anyway, so there is some local to global principle. And then what about the mirror of invertible polynomial? So we can do it for the two variable case. So in this case, we have f is one of the three polynomials, and the transpose is the same as f in Fermat and loop cases, and the chain case slightly different. So you recall that what you do is you write the exponent into a matrix P01Q, and then you take the transpose, and this is P10Q, and this is the corresponding polynomial. So what we want is we want some discounting. We want discounting to go from here to here. So can you express this as a discounting of something here? So this is a joint work with another set of my students, Dong Ja and Chang. And so the step is, first you look at Miller fiber of F. Oh, sorry, maybe let's go ahead. Some minutes. No. Let me just write the steps and finish. And you consider quotient, maximal quotient, and the mirror. And then this guy has mirror given by this discounting. It's given by x to the p's, y to the q's, plus xyz, y to the q's, plus xyz, z xyz. And then, so this is what we did here. And then to obtain the transpose polynomial, the transpose, if you set z equals 0 in the first case, second case, z minus y to the q minus 1 equals 0, z minus x to the p minus 1 minus y to the q minus 1 equals 0. So you have some relations of g, x, y, z equals 0. So you could kill this, then this is transpose. If you say z equal y to the q minus x to the q minus 1, x to the q minus 1, then it becomes, x to the q minus 1. So many typos. It's x to the p minus 1, then this is x to the py plus y to the q. So that's the transpose. And this is a transpose loop. So the question is, what is G? And another question is, what is the restriction? So why do you restrict to z, x, y, z equals 0? And the answer for the first question is that this is both are related to monodromy. So this is monodromy of F, and this is this is like restriction is kind of mirror to variation operator. But unfortunately, I don't have time to explain. So what I'm saying here is that from the monodromy, you can obtain G as another discounting. So this can be obtained as another discounting. and related to this variation operator of the singularity, and the restriction is near to taking actual variation operator. So that's how one obtains a transpose polynomial using symplectic geometry. Let me stop here.